Hello everyone, I'm Agnes, a doctoral student at the CIPHR research group at the Institute of Physics, University of Tartu, Estonia. I'm super excited to discuss with you all a fascinating development in imaging technology, introducing two advanced algorithms, nonlinear Lucy-Richardson algorithm 1 and nonlinear Lucy-Richardson algorithm 2, which brings a significant improvement to core aperture imaging. Why was it necessary to introduce these algorithms? Do you all know that you don't always need a traditional lenses to capture an image? Imagine being able to take a photo using just patterns of light and some clever math. Think of it like this. Instead of using a lens to focus light, we use some specially designed patterns called coded masks to scatter the light in a predictable way. Then, using some computational reconstruction methods, we unscramble these patterns to recreate the image. It's like solving a puzzle where the pieces or the scattered light pattern and the algorithm puts them together to reveal the picture. However, the imaging quality achieved through coded mask has historically lagged behind that of direct imaging in both visible and non-visible regions of the spectrum. To address these challenges, this research work aims to advance the field of Sky by developing advanced computational reconstruction methods capable of producing the image quality comparable to direct imaging. This research targets two critical electromagnetic regions, the highly developed visible spectrum and the less developed mid-infrared spectrum. Additionally, it seeks to expand Chi applications beyond the 3D space to the spectral domain, enabling mid-infrared fingerprinting applications such as melanoma diagnosis, food adulteration detection, and industrial process monitoring. Chi was extended for 3D imaging of objects with incoherent light using a new holography technique called interference-less coded aperture correlation holography (ICOACH). ICOACH enabled applications such as image resolution improvement, field of view extension, partial aperture imaging, depth of field engineering, and imaging through scattering layers. This research work aims to overcome these challenges by developing these advanced algorithms to match the signal-to-noise ratio of direct imaging for ICOACH and Chi. So let me start with a glimpse about NL-LRA1. The NL-LRA1 algorithm for limited support images starts with an initial guess IRN, which is set as 1, to I0, as I0 is often close to the real solution, improving the stability and the convergence speed. The algorithm uses the ratio of I0 to the estimated solution I0 prime, providing the information on how far the current solution is from the actual one. Then this ratio is non-linearly correlated with the IPSF to compute the residue, which is iteratively applied to redefine the solution. A mask with ones within the object area and the zeros elsewhere further enhances the correction, accelerating the convergence rate. This approach has improved the convergence speed by nearly 70%, often achieving results in just one iteration for specific cases and revealing the performance of non-iterative reconstruction methods. Next, let us discuss about NL-LRA2. NL-LRA2 is designed to improve the performance of NLR within LRRA by minimizing the entropy of the output matrix through a sparse search algorithm (SSA). Unlike NL-LRA1, which uses a partial object information for optimization, NL-LRA2 is a blind method that focuses solely on reducing the entropy by iteratively adjusting the pixel magnitude of the spectrum while maintaining the phase. This approach enhances the solution of NLR by entropy optimization, balancing the performance and the execution time depending upon the sparsity of the search. So compared to NL-LRA1, NL-LRA2 achieves high signal-to-noise ratio and better outcome in extreme conditions even with the limited iterations. Next, The India algorithm also complements NL-LRA1 by leveraging the spectral phase information by applying the magnitude constraint to iteratively refine the object reconstruction. Together, these methods demonstrate a significant improvement in image reconstruction under challenging conditions. So now let us see few simulation results. The simulations were conducted to validate these algorithms under diverse scenarios. NL-LRA1 showed a remarkable of 70% improvement in the convergence speed compared to LRRA, achieving an optimal results in fewer iterations. For NL-LRA2, the entropy values were significantly lower even under extreme conditions, showcasing its capability for high-quality reconstruction. Different simulation tricks has been trialed out to verify both NL-LRA1 and NL-LRA2, and you can check it out in our supplementary section. Now let us discuss few of the experimental results. As I mentioned earlier, experimental verification has been done for both highly developed visible spectrum and the lessly developed mid-infrared spectrum. Firstly, let us discuss about the optical experiments with visible light and spatial light modulator. This is the optical experimental setup that we used for our research work. The setup consists of two units, illumination unit and a recording unit. In the illumination unit, we use a high power light emitting diode LED from Thor Labs. After that, we have two lenses to modulate and critically illuminate the object. Light from the object is collimated using another lens and it enters into the spatial light modulator, which modulates the light, where we display the face mask and the intensity distribution is then recorded by the image sensor. First, we record the PSF using a pinhole and then we replace the pinhole by the object and we record the object intensity distribution. Now, let us discuss few results for proving NL-LRA1. Here are the reconstruction results for verifying NL-LRA1 with limited support images. In the study, we recorded a PSF and the object using a digit 3. Row 1 showcases the face mask, row 2 shows the IPSF, row 3 shows the I0, row 4 shows the reconstruction results for NLR, row 5 for LRRA and row 6 for NL-LRA1 and finally row 7 for India. To evaluate the performance, we used different coded masks including a diffractive lens, a diffractive axicon, a cubic phase, a quasi-random lens and a spiral axicon. From the reconstruction results, it is clear that NL-LRA1 outperforms all other reconstruction methods. To quantify this improvement, we calculated the entropy and plotted the results for various coded masks. These plots demonstrate that NL-LRA1 achieves the lowest entropy and lowest RMSE compared to other methods, confirming its superior performance. Interestingly, the performance of India is nearly identical to NL-LRA1 in these tests. This is because the noise level in NL-LRA1 is relatively low, allowing its amplitude and phase information to be effectively used at the input for India. This study highlights that NL-LRA1 not only improves the reconstruction quality but also serves as a robust foundation for further optimization using these methods like India. Next are the reconstruction results for verifying NL-LRA2 with full view images. The experimental results with digit 3 and digit 1 is used to demonstrate the performance of NL-LRA2. Row 1 shows the IPSF, row 2 shows the I0, row 3 shows the reconstruction results for NLR, row 4 is for LRRA and row 5 is for NL-LRA2. For different coded masks like diffractive lens, diffractive axicon, cubic phase and quasi-random lens, and finally spiral axicon with a topological charge of 5. The direct image of the object we used is shown at the bottom of the image. NL-LRA2 consistently achieves the lowest entropy and lowest RMSE with fewer iterations than LRRA except for the diffractive lens. where the iteration required are similar but with slightly higher RMSE. The advantage of NL-LRA2 lies in its ability to optimize entropy blindly, yielding a superior signal-to-noise ratio and quality results, although it does not necessarily reduce the execution time due to the entropy optimization process. The study highlights a trade-off between the computational cost and the entropy, with a sparse search reducing cost but slightly increasing entropy. Next, let us discuss about the experimental results with infrared light. The experimental set for infrared imaging involves an infrared source from Thor Labs controlled by a power controller and an iris for light regulation. The light is focused by a concave mirror onto a 200 micrometer pinhole collimated by a plano-convex lens and directed to the fabricated DOEs like diffractive axicon, cubic face mask and quasi-random lens, and the results are recorded by an IR camera. For this experiment, 2 points were used as an object. Two 200 micrometer points are separated by 2 mm and the holograms were recorded for reconstruction analysis. The results of the IPSF and I0 are shown in column 1 and column 2. And the reconstruction output like NLR, LRRA and NL-LRA2 are discussed in column 3, 4 and 5. The entropy and the iteration analysis indicates that NL-LRA2 outperforms LRRA across all the DOEs, requiring fewer iterations and yielding better entropy values. Now, to evaluate the NL-LRA2 performance, optical experiments has been conducted using a commercial IR microscope with a Globa TM broadband IR light source and a synchrotron IR radiation. The experiments were recorded and the IPSF and I0 for the test object includes a cross-shaped object and a random pinhole object. And for the commercial microscope, NL-LRA2 required fewer iterations like 25 iterations for in case of cross-shaped object and 14 iterations in case of a pinhole and achieved a lowest entropy compared to LRRA is shown in figure A and C. Using a synchrotron radiation with a cross-shaped object was imaged and using NL-LRA2 also achieves an entropy reduction in fewer iterations like in case of 6 iterations than LRRA is shown in figure B and D. Across both setups, NL-LRA2 consistently outperformed LRRA, confirming its efficiency in achieving high-quality infrared imaging with reduced entropy and reduced iterations. Now, to test the practical application with NL-LRA2 in challenging scenarios, a complex natural object like a leaf and a scenery image was imaged using a smartphone camera. We used to capture an image using iPhone 15 Pro Max and we adjusted a low f-number setting producing a blurred images. Using synthetic PSF, we generated for those images and NL-LRA2 was applied for reconstruction with results compared to other reconstruction methods. For both the objects, NL-LRA2 required fewer iterations like 7 in case for the leaf and 6 in the case for scenery and achieved a least entropy as you can see from the figure. Despite the weak blur in the scenario, NL-LRA2 outperformed LRRA and other methods, delivering a better reconstruction quality, and this experiment demonstrates NL-LRA2's effectiveness even in practical and minimum blurry cases. In conclusion, NL-LRA1 and NL-LRA2 set a new benchmark in computational imaging, addressing the key limitations of existing methods. Their applications can be extended to live cell imaging, high-speed imaging, computer tomography, and more. Looking ahead, these algorithms pave the way for further achievements in coded aperture imaging, enabling more efficient and high-quality imaging across various fields. We hope this work will inspire further exploration and innovation. Thank you so much for your attention, and our work has been published in the prestigious journal Optics and Laser Technology. At this moment, I would like to express my heartfelt gratitude to my supervisors, Professor Vijay Kumar Anand and Professor Joseph Rosen, for their invaluable guidance, support, and encouragement throughout this work. Also, I would like to thank all the collaborators and the advisors of this research work. If you have further questions, thoughts, and feedback, please feel free to write to us. And please check the description for more details. Science is all about the collaboration and curiosity, so let's keep exploring together. Thank you and see you in the next talk.